All right, hi kids. So today what we're going to do is we're going to go over properties of exponents. This is a nice little review of things that you did in Math 1 or even in 8th grade. Just kind of going over this again. Video lessons. You'll be doing these on days that I'm not here or days that we have quizzes or tests, something short. Um, Understand that it is a video. You can pause it, write, rewind, all that stuff. If you are getting it and you want to speed ahead, feel free, go ahead. But again, this is always here for you to reference and go back over. I really find these to be helpful for students who need a little bit more time or time to absorb material. So again, with your first video lesson, I'd appreciate it if you've listened to all of it, took down your notes, and then made sure that if there's anything, you go back and re-listen to it or ask Miss Naska tomorrow, just any questions that you might have. So here we go. These are just the properties of exponents that you should have learned last year. If not, you're going to learn this year. So the first one is the product of powers, which virtually means that you are multiplying two terms that are raised to an exponent, but the term has the same base. So just really quick, all right, so if you had a to the mth power, this is what we call the base, all right, and m is what you call the exponent or power. All right, it's another name for an exponent, but we use powers just to make things a little bit easier here. But so these properties work when you have the same base or the same variable or number that is your base, or the big term or the big value in here. All right, it's the big letter, a big number. The small numbers, those are your exponents. Those are either being added, multiplied, subtracted, and so forth, so on. So anyway, product of powers means that when your bases are the same and you're multiplying the two together, you actually are in fact adding the exponent. So for instance, if we did like x to the third times x to the second, all right, because x's, the bases are the same, all you do is you add the exponents. 3 plus 2 is 5, x to the fifth power. And that's what the product of powers property is. Now, do you need to know what that's called? No. Is it helpful? Kinda. But it's understanding that in this case, you're not multiplying the exponents together, you're adding the exponents together. You're just counting how many of that base you have. So the next one, power of a power property. So if you look here, I have these rules here. So a to the mth power raised to the nth power is the same thing as going a to the mth times n. So in this case, you're actually multiplying exponents together. So I should show this a couple ways. So some kids are like, oh, I get confused when I see multiplication in between, like you saw in the top one. Do I add or multiply? And here, what I like to do is I like to show it like this. Anything like, for instance, this little like side note over here. All right, if you were to see this like 3 times x plus 2, sorry. All right, oops, I don't know why that's moving around. All right, come on, buddy, stay there. All right, 3 times x plus 2, that's an x. All right, this should be telling you or screaming to you, oh man, I need to distribute. All right, because you see that parenthesis there. So any value that is adjacent or right next to a parenthesis with no addition or subtraction sign means you're going to multiply that in there. So my exponent, because there's nothing in between that exponent and the other exponent, that means we're going to distribute it virtually to that other exponent, and you're going to multiply that. All right, so for instance, if you saw this, like x to the third power, all raised to the second power, all right, you have a power raised to a power, or power of product, power of powers property. This is really going to be x to the 3 times 2, which is x to the 6th power. All right, so again, just being able to see this, remember these different things. Now, this is a power of a product. So this next one, it's really just a step forward. So this, notice the difference between this and the top one is that you have actually two different variables in here. So a and b. Now, a and b actually, in fact, have exponents on them themselves, but you don't see them. Anytime you see a variable without an exponent, that means it's raised to the first power. So this is actually kind of really emphasizing my explanation above about the distributing. Anytime you have two different values or multiple values inside there that are all being multiplied, notice product, all right, means everything's being multiplied inside your parentheses. All of these are going to actually get that exponent distributed to it. So a times b, all raised to the nth power, is really a to the mth power times b to the nth power, because really there's a 1 out in front of these little exponent of m's. You see that? So let's see an example of this. So ready? If you had x squared y to the third power all to the fourth power now. So now you have two terms raised to two different exponents. What you're going to do is you're virtually going to distribute that exponent to x squared and y to the third, and you're going to get x. Now you're multiplying squared times 4 and y to the third times 4, and you're going to end up getting x to the 8th, y to the 12th power. All right, because a power of products or a power raised to a power, you multiply that exponent to every other term's exponent. All right, so power of a quotient. So this power to a power or product of powers, you're adding and multiplying, you're making things bigger. But what if you're distributing or dividing, quotient, dividing, all right, terms, and it's raised to an exponent? Well, this is the same thing. You're going to distribute this exponent to both the numerator and the denominator. So a divided by b to the nth power is really a to the nth divided by b to the nth. So again, I like using x's and y's to hopefully help, emphasize my point. So if we did this, x to the fourth, x to the fourth over x squared. Now, one thing, I'll go y. I'll change this to y because it'll just make things a little bit easier. Let's make this to the third power. All right, all you're doing is distributing that exponent to the numerator and denominator, so you're going to get x to the 12th over y to the 2 times 3 is 6. And notice this is as far as you can go because your bases are different. Your bases are x and y. You can't add them, you can't multiply, you can't divide, you can't do anything with them because you have different bases. All right, all you did is distributed that exponent. Now, with that said, I kind of paused for a second. The difference between power of a quotient property, this guy, and then the next one, quotient of powers property. Again, the names really don't matter. It's what you see is different. You should notice that, hey, this is a over b, whereas down here it's a to the nth power over a to the nth power. Notice, these bases are the same. Bases are the same means that we can simplify this further. So if you see two terms raised to an exponent, but the bases are the same, you can subtract their exponents, numerator minus denominator, top minus bottom. So if you had this x to the fourth power over x squared, you're going to subtract the numerator's exponent 4 minus the denominator's exponent 2, and this is going to be x to the second power, simplified. And all this is just using these different tools of exponents to simplify the values that you see, the terms that you see there. So, all right, let's keep going. I believe we have two more. Now, all right, we have something called the negative exponent property. So any base that's raised to a negative exponent, you cannot leave that as an answer. You cannot leave negative exponents. It's just bad math to leave a negative exponent. So anytime you have a negative exponent, whether it's just a straight up negative exponent or in fractional form, 1 over a negative exponent, you need to get rid of that negative exponent. Now, it just doesn't disappear. What you have to do is you have to do something that I call move it or lose it. All right. Now, one thing that I do is I actually kind of tell this as a story. So I'm going to tell you a story on the computer right now. So I have 2 little kids at home, and this actually happened with my firstborn, and it like clicked one night because I was like on like 45 minutes of sleep, where I thought about how do you explain negative exponents. All right, so number one, all exponents or all terms with an exponent can be written as a fraction. So I'm going to start with this first one, and I'm going to put this a to the negative nth over 1. Now my story goes with upset children, negative children, children that are negative in how they're behaving. Like when my daughter was, colicky when she was younger, she used to cry. And what I'd have to do is I had to figure out ways to get her to calm down. And I found out that when she was on the second floor of her house and she was crying, what I'd do is I'd walk downstairs, down our flight of stairs, and go to the first floor, and to become happy or positive. So what that means in the story is if you have a negative baby in the numerator, to make it positive or happy, you move it to the denominator. You move it to the opposite location. So a to the negative nth, to get rid of that negative exponent, you move it from the second floor to the bottom floor, and it becomes positive. But what do? You can't just put a number in the denominator and leave it. What you have to do is you have to put it over 1. All right, you put it over 1. Now, don't get in the habit of always taking this denominator and just shoving it right up in the top, because eventually what we can see, and I'll give you a side note because I like showing kids some cool things, but not freaking them out. If you had a to the negative second power times b to the positive first power, let's just leave it like that. The negative is what we have to get rid of, all right? This guy. So what we're going to do is we move that to the denominator, so it should be a to the positive seconds in the denominator, but b to the first because that exponent's happy, all right? Understand, if a baby's happy, you don't move it, you don't touch it, you leave it where it's at, so that b to the first power would stay there. All right, so it doesn't mean that 1 always goes in the numerator. It's just you can't leave a value with the denominator and no numerator. So there has to be a 1 there to represent a spot for the numerator. So to the second part over here, what if you start off with a negative exponent in the denominator? Well, again, you have to move it. So the baby's unhappy on the first floor. You have to move it to the top floor, and you put it over 1. So it'd be a to the nth power. So an example would look like this. If you had x to the negative third power, well, first off, you put it over 1. You say, oop, unhappy baby in the top, we're going to move it to the bottom. So x to the positive third power, and then what goes in the top? 1. Not because the denominator was 1, but you have to have a value of 1 there if there's nothing else in the original problem. All right, same thing. We can have another one where you saw like 1 over x to the negative fifth power. Again, negative baby in the denominator. We're going to move that up to the numerator, x to the positive fifth power. You could put it over 1, or you could leave it, honestly, as x to the fifth power, because you don't need to put it over 1, because any value, when it's converted from a fraction to a whole number, you don't need to put it over 1. It's just known that it's over 1. All right, and the last is a zero exponent property. And here's the deal. Anything raised to the 0 power, anything raised to the 0 power equals 1. All right, so if you had 5 to the 0 power, it equals 1. If you had negative 3 to the 0 power, all right, notice I put parentheses around it, it equals 1. If you had negative 3, like this, raised to the 0 power, check this out. It's not 1, it's actually negative 1. All right, because technically there's a 1 here times this. The negative is not raised to it, just the 3 is, so this would actually be negative 1. Now this is fun little honor style math, but anyway, one thing that I always do just to express my point, smiley face emoji raised to the 0 power is 1. Okay, anything raised to the 0 power is 1. So with that said, we're going to do a couple examples using our relearned or reviewed exponent properties to make sure we know what's going on. So let's start with number 1. So we have a to the third power times a to the 7th power. So this is a power of, what's the name? I just want to, product of power. So basically we are multiplying two terms with exponents. So we don't multiply them, we add them together. So it's a to the third plus a to the 7th, or 3 plus 7, which is a to the 10th power. All right, number 2, really quick, anything to the 0 power is 1. That was easy. Now, number 3. Now, what I'm going to do is I'm going to actually ask you to pause the video. I want you to try number 3 and replay it in a second and see if your answer matches mine. All right, so ready? So this is a product of powers because we have x to the third and y to the first power, all raised to the third power, which means that this exponent of third needs to be distributed to both. So we're going to go x to the third times 3, y to the first times 3, and then we simplify this. And it's going to be x to the 9th, y to the third, and that is simplified. All right, so let's do this. Pause this next one for 4, replay it when you're done. All right, number 4. So x to the 10th divided by x to the 7th. So this is a quotient of powers. So that means that we have the same base and we are dividing these, which means we're not really dividing it. We're actually going to subtract numerator exponent from denominator exponent, and you get x to the third power. And if you got that, that's awesome. If you didn't, we'll keep practicing. Don't worry. So here we go. Number 5. Now, this is the first time that we've seen this on this worksheet where your base isn't a letter, it's not a variable, it's actually a number, and that's totally fine because numbers and variables can all be raised to a power. The thing is, though, when your base is a number, I want you to simplify your answer as a number itself. Don't leave it as, 2 to the 12th power or whatever. I always say a joke like this: when you guys get older, for some of you, you're almost this age, you don't go around on your sweet 16 saying that you're 4 to the 2nd power. If you do, kids are probably calling you nerds like I was. But anyway, you just say it's my sweet 16th. You don't say it's my 4 to the 2nd birthday. All right. So with that said, anytime you have your base that's a whole number or a number itself, make sure you just simplify that. So with that said, number 5, it's 2 to the 4th times 2 to the 5th. Very similar to number 1. This is a product of powers. So what this is really 2 to the 4th plus 5, which is 2 to the 9th. Now, before you say, all right, I'm circling and I'm done, we're going to take out our calculator. This isn't one you can't really do. All right, but 2 to the 9th, or 2 times 2 times 2, 9 times together, you should get 512, and that is the answer I'm going to look for. But I will tell you this work that you could show, 2 to the 4th plus 5 equals 2 to the 9th equals 512. That is great work to be shown. All right, let's try this one. Let's go to 9 and 10. So I'm going to do a couple more, and then I'm going to ask you to pause the video, do the rest of the examples, and then play it to see my answers. All right, so let's try number 9. So number 9 is a quotient of powers. Quotient of powers means we're going to subtract numerator 7 minus denominator 13. Now your answer is going to be x to the negative 6th power. Now you're like, yay, I did it, yay. Unfortunately, that's not correct, because you never want to leave an answer with a negative exponent. So what we have to do is we have to say, yes, we did do the quotient of powers, but we didn't simplify the negative exponent, meaning that we're going to put this over 1, and we're going to say we're going to move this unhappy baby. Now, I'm going to have to put the work over here. So since x to the negative 6 is in the numerator, x to the 6, positive 6, will go to the denominator, and we put this over 1. And this is proper math and a proper answer. All right? And then number 10. Now, I say let's do number 10 for this reason. Take a look at this guy. 3 to the negative 2nd power, and then all raised to the negative 4th power. Now you're like, oh man, I should just change it and move it all together. I always tell my students this. There are times when you want to do that and times not to. In this case, you're not going to want to, because this is a product, or sorry, not a product, but a power raised to a power. We have this negative 2nd raised to the negative 4th. And what that tells me to do is I'm going to distribute or multiply these exponents together. Now, our multiplication rules say negative times a negative is a positive, which actually means that our answer is going to be 3 to the 8th power, a positive exponent. So do we need to move that exponent anymore? No, turn positive. But we do need to simplify this answer. 3 to the 8th power is 6,561. Bam, that's your answer. All right. If you scroll down, you look at these other ones. I think these are fun challenge ones, like 16. Oh man, we have 3 terms here. Oh boy, your rules stay the same. All right. You have 3 terms, all the same base. What you have to do is just do your proper math. When you multiply terms with the same base that have exponents, you add their exponent. So here's the deal. Pause the video, try 6, 7, 8, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And then when you're done, replay the video and you can check my answers, okay? All right, pause it now. All right, so here you go. Take a look at these answers. As you go through it, I just pause it and check your answers. One big thing, look at 19. It was d to the 0 power. Now what I did is I knew d to the 0 power was 1, so I actually just got rid of it. I didn't even worry about it. So all I worried about was 2 to the 3rd power and d to the 5th power. I got rid of d to the 0 power. Didn't really care. One last thing before we flip over. Anytime you're doing one of these problems, all right, and this is the only like caveat to the base being a number. If the base, it's okay, buddy. If the base is a number, and when it's raised to the exponent, and when you put it in your calculator, you get like 2 point blah 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 e to the something. That's scientific notation. That's a calculator's way of saying that that number is humongous and we can't get it on our screen. So if it does that, anytime you see the e to e10 or e50, whatever it is, just say, all right, check. I'm not going to put that number, I'm not going to convert that exponent as a number. I'm just going to leave that as like, for instance, like, let me give you an example, like 1 over 10 to the 15th power. If you were to put that in your calculator, it would go 1e15. You're like, what is that? Don't put 1e15 on your test or quiz or homework. Just leave it at 1 over 10 to the 15th. Don't leave it as 1e15. So if you type that in, you'd be like, oh, okay, I see what it is. I'm going to leave it like this. Now, would I ever give you one like that? Probably not, but it's always good to know that just don't put 1e15 because that just looks like you have no idea what's going on. All right, flip the page. So a little review. Again, you know, it's always fun going back over things that you learned in the past, and this is the Pythagorean theorem. All right, and the Pythagorean theorem is the way that we find side lengths of right triangles. So the Pythagorean theorem is this guy, a squared plus b squared equals c squared, and this is the key. C is always your hypotenuse, the longest side. Now this is the funniest part. If you're like, well, what if x is your hypotenuse? Well, how do you know? Well, here's the deal. The hypotenuse is always shown to you. It's always pointed to you by an arrow, and the arrow is your right angle. The right angle of the triangle, that little box, points always at your hypotenuse, which is C. So I always label what my C is first, and then I say, all right, well, my other two sides have to be A and B. And A and B, because you're summing the squares of them together, it does not matter. So I'll call this A, and I'll call this B. And now some of you are like, whoa, Mr. Grauman, I made 4B and XA. It doesn't matter. You're going to get the same answer. Because now that you've labeled them, you can set up the Pythagorean theorem and solve. So you have A squared, so 4 squared, plus B squared, which is X squared, equals C squared, which is 13 squared. Now, we're going to solve for the value of X by simplifying these values. So 4 squared is 16, plus X squared equals 13 squared, which is 169. We're going to subtract 16, and you're going to get X squared equals 169 minus 16, which is 153. Now, what I want us to do is I want to leave our answer as an exact answer. So to solve this, every time you do the Pythagorean theorem, you are not looking for x squared, you're looking for x. So you have to do a square root. You're going to take the square root of both sides. And your answer is going to be x equals plus or minus the square root of 15. Or sorry, the square root of 153. Now 153, if you put this in your calculator, it does not simplify to a whole number. It would be a decimal. Now, you haven't really gone over simplifying radicals yet. That will be next week, Friday. So what we're going to do is we're going to leave it as the square root of 153 right now. But notice that I put plus or minus the square root of 153. Anytime you take a square root in an equation, you actually get two values. You get a positive value and a negative value. But let's be smart math students here. Can you have a negative side length? We are talking about a triangle here. All right, think about if you were trying to make a house or something and using this. Could you have a negative side length? The answer is no. So we get rid of this negative, and your answer is just x equals plus, or you don't have to leave the plus, the square root of 153. And that's your value of x. All right, so let me do this. Pause for number 2. Try it and see if you get the same answer as me. All right, here we go. First off, you should have identified what your C is. X is actually C in this problem. We'll make A 6 and B 15. So to set up the Pythagorean theorem, you're going to go 6 squared plus 15 squared equals C squared. And we'll just simplify. So 36 plus 225 equals C squared. So 36 plus 225 is 261 equals C squared. And just checking really quick, I'm pretty sure that this won't work out, because to take the square root of both sides, the square root of 261 is a decimal, so we're going to leave our answer as C is equal to, now it should be plus or minus the square root of 261, but we're saying, hey, you can't have a negative, so it's really just C equals, or in this case, I apologize, XC. I just always put it C, I don't know why it is, but C, really we should just convert that to X. All right, convert these to X's, I apologize. All right, and X equals this, and that X in this case is your longest side. It's your hypotenuse because it was across from the right angle. All right, so your homework tonight, yes, you have homework, is the bottom problems down here. All right, a couple Pythagorean theorems, a couple properties of exponents to test out whether or not you actually were paying attention to this. While you're doing this, if you have any questions, you can go and see Ms. Naska in the morning. Otherwise, you could check your answers on Google Classroom. As you're going through this, I would encourage you, after each problem, go and check your answers and to make sure that you're doing it right. If you're not doing it right, go back and check your notes on the other side. All right. Have a great day, kids.